Hey guys, welcome back. This is Physics for Life Science, and in this video we're going to be talking about the constant K found in Coulomb's law. So as in the previous video we were talking about the constant found in Coulomb's law, and in reality what that means, or what it breaks down to, is 1 over 4 pi epsilon. Now you may be wondering, what in the world is epsilon? Well, that's just the permittivity of free space. And you may be wondering, what in the world is permittivity of free space? The way you can think about this is it's the resistance to form a magnetic field in a vacuum. So pretty much the same way we found moment of inertia in the first semester physics. That's pretty much what epsilon is. It's the resistance to form a magnetic field in a vacuum. So based on that, epsilon is given the value of 8.85 times 10 to the negative 12 coulombs squared over newtons times meter squared. All right, so now you can go back and forth between the formulas. So if we plug in K into our force formula, we'll find that it's 1 over 4 pi epsilon times charge 1, charge 2, and the distance between the charges. All right, sometimes the permittivity of free space may change, but most of the time it doesn't, just for the simplicity of physics too, it doesn't. So don't worry about that. However, some problems may have you. They may tell you the force, they may tell you the distance, and the charges, and they may want you to find the permittivity of free space. So now it's just a matter of rearranging it. But most of the time it doesn't, because again, it's a constant. And in physics too, we don't talk about things varying. We most of the time talk about situations where everything is perfect, in ideal situations. That's why I'd say it in a vacuum, right? In an ideal situation. So that's what you need to know about this. Another thing I wanted to point out that I didn't have time to address in the past video was the fact that you're going to be seeing a lot of E's in this chapter, in this section of the semester, especially with Coulomb law. And the variable E, we're used to thinking about it as an electron, right? It's like, oh, an electron, yeah, I see an E, I know it's, an electron with a negative charge. However, in this case, in this realm of physics, we're using E not to denote that it's negative, but rather to refer to its charge, which is approximately 1.6 times 10 to the negative 19 coulombs. And now this is why I was saying 1 coulomb is almost very hard to find, because you can imagine how many electrons would have to be concentrated in 1 coulomb, right? So that's why in electromagnetic forces, we're going to be dealing with very small forces. So we're referring to this charge itself, 1.6 e to the negative 19. So now when you're going to see positive E, that is not referring, this is going to be a proton, but we're not going to be referring to the mass. So we're not going to be referring to the mass. What we are referring to is the charge. And the charge of an electron and the charge of a proton are equal. Now you maybe remember, no, I thought it wasn't equal. I remember from chemistry. What you remember from chemistry is the masses being different. The mass of a proton is way greater than the mass. So mass of an electron and mass of a proton, they are not equal. What happens is the mass of a proton is way greater than the mass of an electron. That's what you may be confusing this. But in physics for electromagnetism, we're going to be using E denoting the charge. So whenever you see a positive E, that's just going to mean positive 1.6 e to the negative 19 coulombs. When you see negative E, that just means 1.6 e to the negative 19 coulombs. And as I said earlier, this is referring to a proton. This is referring to an electron. So you may be given a proton and an electron, like the case we worked earlier. So the proton will be a positive charge. The electron would be a negative charge right there. So now, based on this, I hope gives you a little bit of clarification when you're working problems. Also, I just wanted to quickly point out that this formula kind of resembles what we touched earlier in first semester physics, where the force, remember the general gravitational force, where it was, so gravitational force, remember that it was F equals G constant, big G, times mass 1, mass 2 over the radius squared. So they're very similar, right? And it's because in physics, or just the laws of the universe, everything behaves very similar in the big scale as in the little scale. Some rules may bend, especially when we're talking about electrons, but you'll see that in further videos that we address that. But for now, most of the things that apply to big scales, such as planets, apply to small scales, such as charged particles, which I honestly think it's incredible. And it just shows how the universe it's made up by rules. So I hope this video helped you out. And remember, if you like it, please leave a comment, like us on Facebook, on YouTube, and remember to please check out our website. It's free. It's physicsforlifescience.org. It's right there, where you can find the home. You can find all the videos, all the videos that we publish. You can find the mission statement, our vision, how to contact us on Facebook and YouTube. So yeah, just please check out our website, like us on Facebook, and good luck with your study, guys.